You know when you grab a battery, any battery, and you see that little V on the side? Ever stop and wonder what that actually means? Well, today we're going to decode it. We're going to figure out how this thing called voltage really works inside the electronics that pretty much power our entire world. So let's get right into it.
So let's start with something we all know, the battery, right? These little power packs are literally everywhere, and they hold a really fundamental concept of electricity right there on the label.
Yeah, we see these numbers all over the place. Your TV remote probably takes one of these, a 1.5-volt battery. A smoke detector, on the other hand, might use this blocky 9-volt one. You got different numbers, different shapes, but that V is always there.
So what's the deal? What is that V for volts really telling us? I'll give you a hint. It's not about how big the battery is, or even how long it's going to last. Nope. It's all about the electrical push that it can provide.
Alright, so let's get a really clear definition. Because honestly, if you can understand this one concept, it is the key to unlocking how basically all electric circuits work.
Okay, so scientifically, the fancy term is potential difference. I know, it sounds a little complex, but it's really just a way to measure the energy difference between 2 points. A great way to think about it is like water pressure in a hose. The higher the pressure, the stronger the push, the faster the water comes out. Well, voltage is just the electrical version of that pressure.
Thankfully, you don't have to go around saying potential difference all the time. Phew, we just call it voltage. So a 9-volt battery gives a much bigger electrical push than a 1.5-volt battery. It's really as simple as that. Okay, so we get what voltage is. It's this electrical push, but how do we actually go about measuring it inside a real circuit? Well, for that, you're going to need a special tool.
And that tool is the voltmeter. And just like pretty much all technology, it's had a bit of a glow up. We've gone from these older analog models with a little needle on a dial to the super precise digital displays that we use today. But no matter what it looks like, it does one job and one job only. It measures voltage.
Now, listen up, because here is the #1 golden, most important rule for using a voltmeter. You always connect it in parallel. What does that mean? It means you don't break the circuit. You just connect the meter across the component you want to measure, giving the electricity its own separate path to go down.
Now, this is the complete opposite of its cousin, the ammeter, which measures current. See, an ammeter has to go in series. You actually break the circuit and force all the electricity to flow through it. A voltmeter goes in parallel, measuring the difference across a component. Two totally different tools, two totally different ways to connect them.
And that brings us to the main event. Because how voltage behaves depends completely on whether the circuit itself is built in series or in parallel. And believe me, the rules are complete opposites, so let's get this straight.
First up, a series circuit. Think of this like a single-lane road. All the cars have to follow the exact same path, one right after the other. In electronics, it's the same idea. All the components are just lined up in one single loop. And here is the rule you have to remember. In a series circuit, the total voltage from the battery gets shared or divided up among all the components. So if you've got a 3-volt battery and 2 identical light bulbs, each of those bulbs is only going to get 1.5 volts. They have to share.
But what about a parallel circuit? Well, this is more like a road that splits into multiple lanes, like a highway. The cars can choose different paths, but they all start at the same place and they all end up at the same destination. In this case, the rule flips completely on its head. The voltage is the same across every single branch. So, with that same 3-volt battery, every single component on every separate branch gets the full 3 volts. This is an absolute game changer of a difference.
Okay, I know that was a lot of information, so let's pull it all together into one simple little cheat sheet, and then we're going to put our new knowledge to the test.
Now, what's really cool about this, and what I want you to see, is the beautiful symmetry of electricity. Do you see the pattern? In a series circuit, voltage gets shared, but the current, that's the flow, is the same everywhere. But in a parallel circuit, it's the total opposite. The voltage is the same everywhere, but the current is what gets shared among the branches. If you can remember this inverse relationship, you've cracked the code to understanding circuits.
All right, time for a little pop quiz. Here are 4 circuit diagrams. Each one has a voltmeter, that's the one with the V, and an ammeter, the one with the A. Based on those rules we just covered, which of these diagrams, A, B, C, or D, is wired up correctly? Just think back. Ammeter in series, voltmeter in parallel. Which one is it?
And the correct answer is A. So why is it A? Well, look closely.
The ammeter is in series. It's part of that main loop, forcing all the current to flow right through it. And the voltmeter? It's in parallel, connected across the resistor to measure the voltage. It perfectly follows our two golden rules.
Okay, let's wrap this up with one last puzzle, something to really test your skills. Now, this circuit is a little more complex. It's actually a mix of both series and parallel parts, and it's all being powered by a 6-volt battery. So here's my question to you. If that main battery is putting out 6 volts, what do you think the readings on V1, V2, and V3 are going to be? You'll have to use the rules for both series and parallel circuits to figure this one out. Give it some thought, because once you can answer a question like this, you can pretty much decode any circuit you come across.